Hey there, AP Calculus students. This is Mr. Bean, and today's lesson is going to be on optimization. Calculus has its tendrils in lots of different fields: economics, business, medicine, all sorts of different sciences. And the reason why is a lot to do with this optimization, where we're going to try to find the most or the least of something. And so this is a great lesson to get really good at, because for those of you who have to take a calculus class in your future, a lot of it may be focused on this stuff. So I've got some examples here, and then I'll talk about the strategies at the very end of the lesson. So let's go ahead and just jump into this. Finding two numbers whose sum is 30. So let's just say I've got two different variables, x and y, two numbers that I don't know what they are, but if I add them up, I know I'm going to get 30. And then I also know that their product, so their product is going to be x times y. And I'll just say that that equals some capital P. P is going to stand for product. Now, when we look here, it's saying that this is, what do we want to make as large as possible? The large as possible is going to be this. So that means the large part means, if I were to come down here and kind of think about, I would have some type of maximum value. So when do we have a maximum value of the product? When its derivative is equal to 0, because I'd have a slope of 0, and the second derivative would be negative. So if the first derivative equals 0 and the second derivative is down, to make it concave down, then I've got a maximum. That's what I'm looking for on this. So how do I do that? I have to take the derivative of p to find p prime. But we don't want to do that yet, because I have too many variables, x and y. I just want one variable. So the way we do that is we take our other equation, and let's say that y equals 30 minus x, and I can use substitution now. So I'm going to substitute that into that y. And that gives me what? X times 30 minus x equals p. Let's multiply that out. 30x minus x squared equals p. All right, now let's go ahead and take the derivative of that. So that's 30 minus 2x equals p prime. So I want to figure out, when does the derivative equal 0? So let's say that this thing equals 0. So I would, if this whole thing is a 0 right there, I'd subtract 30, divide by -2, I get x equals 15. So x equals 15, and then let's double check. Is the second derivative, what's the second derivative? Here's the first derivative. So the second derivative is going to equal -2. So it's concave down. The first derivative equals 0, so this is a maximum. So if x equals 0, or x equals 15, y is also 15. There are my two numbers right there. So that first example gave us the basics of how this works. We're going to set up an equation that we want to take the derivative in order to optimize, to find either the largest or smallest of something. And then it can only have one variable. So sometimes you'll need another equation that you can manipulate to plug in to give yourself only one variable. But then you just take the derivative, double check that it's a max or min, and then you're good to go. All right, number 2, what point on the graph y equals the square root of x is closest to 5, 0. So I gave you the graph so you can kind of visualize this. So we're looking for a point along the square root of x curve that is closest to 5, 0. So maybe, is it this point? Is it this point? Is it, oh, obviously it's not that, it's getting farther away. So that's what we're looking for. Well, how do you figure out the distance between two things? You need the distance formula. So this will come in handy for us in today's lesson, in the practice. The distance formula is an adaptation of the Pythagorean theorem. So it's where I have some x value minus another x value squared. So it's the difference between two x values plus the difference between two y values. So I'll say this one y value minus another y value, square it, and then it's the square root of all that. So it's again, it's a variation of the Pythagorean theorem to get the distance. All right, so what are we going to do? I'm going to make a list of my two coordinate points. So I have 5, 0, that's easy. And then my other coordinate point is going to be x, comma, square root of x. So let's see if that makes sense. The other x value is just whatever you plug in, and then the y value is the entire function, that whole thing. So this is the distance that I'm going to be, or the two coordinate points I'm using. So let's plug all that in and see what we get. Okay, so there's my distance formula, and I'm going to have to take, remember, I'm going to need to figure out when the derivative of that, because this is what I'm trying to optimize, I'm trying to find the smallest, the closest, when that distance is the smallest. So when does the derivative equal 0? And then the second derivative should be greater than 0 in order to have a minimum. That's the two things I'm looking for this problem. Let's see, before I take the derivative, why don't I clean this up just a little bit on this particular problem. I think this will help. This becomes x squared minus 10x plus 25. Over here I have plus an x because the square root of x squared. And then this just becomes minus 9x in the middle. So it's this thing with a minus 9x. So the derivative now, the derivative of the distance is going to be, I have 1 over 2 square root of x squared minus 9x plus 25, and then times the derivative of the inside. So now I'm going to have times the derivative of 2x minus 9, the derivative of the inside here. Okay, so that's the derivative. When does this thing equal 0? It's going to equal 0 only when the numerator is equal to 0. So here's the numerator. So we solve that, we get x equals 9 halves. Okay, so if x equals 9 halves, is the second derivative greater than 0? Well, taking the second derivative, this is going to be a real pain. So maybe instead of doing this, maybe what I do is I think, do you remember those charts we did that Mr. Brust showed us how to do when doing some values, doing some test values for first derivative and second derivative test? Let's try the 0.9 halves, because I know if I plug in a 9 half that the first derivative is going to be 0. So what if x is less than 9 halves? And what if x is greater than 9 halves? I'm doing this kind of sloppy, but we're just trying to check real quick. So let's plug in a number that's less than 9 halves, like 0. So 0, 0. I'm just looking to see if it's positive or negative. If I plug in a 0, I'm going to get a negative number. See, 0 here is negative 9, and then this thing's going to be positive. If I plug in a number that's bigger than 9 halves, so like 100, well, if I plug in 100, this whole thing's going to be positive. So if the derivative is decreasing, is 0, and then is increasing, then this is a minimum. So using the first derivative test, I didn't have to use the second derivative test on that one, I can verify that at x equals 9 half, that is the closest coordinate point. So the point is 9 half, comma, and then the square root of 9 half is 3 over square root of 2. And yes, you could rationalize that thing if you wanted. But that is our answer. Okay, Mr. Kelly's making a box to store all his magic cards, and we're going to make the box out of a 14 by 30 piece of cardboard. So let's, over here off to the left, maybe in the margin of your notes, draw yourself a little piece of cardboard. And it is a 30 inches by 14 inches. Okay, so it's 30 by 14. Again, do this off on the left side so you give yourself some more room. And what we're trying to do is cut out some squares. So I'm going to cut out some squares here and here. And all I know is that these squares, that's not really a square, but you get the idea, close enough. These squares are supposed to be equal 4 corners, equal size. So I don't know how big they are, so I'm going to call this a distance of x, a distance of x. Same here, this is x, and so forth. So every little one, this is an x by x square from each corner that we're going to pull out. What size should the squares be in order to create a box with the largest volume? So when it says largest volume, that means we are going to figure out a formula for volume and find the optimal largest possibility. So I'm going to write off here on the side just to remind myself I'm looking for when does volume equal 0, and when does the second derivative, if I want a largest volume, that means the second derivative has to be, it's got to be concave down, so the second derivative should be negative. Or I might have to use the first derivative test with a little chart, depending on the problem. Let's just see how we go. So I know that volume is equal to length times width times height. So we need to figure out length, width, and height of the box if we were to fold these corners up. So this is where it gets a little tricky, kind of visual representation here. Ooh, this is difficult. I will tell you here that, so the volume is going to equal, the length is right here of this box, just this piece, from this end to this end. Well, if the whole thing is 30 on the whole side, if this whole thing is 30 from here to here, then I'm going to take out this piece and take out this piece. So I'm taking out the two x's. So my length is 30 minus the two x's. And then the width, it's the same idea. The whole thing across is 14, and I'm taking out those two x's. So the width of this box is 14 minus 2x. And then the height of the box, if you can visualize folding this thing up, how tall is it going to be? It's going to be a height of x. For the next step, I'm going to save us some time. I went ahead and multiplied this whole thing out so I can see. Honestly, I needed a calculator because those are big numbers. And that gives me 420. So I FOILed this, multiplied it out, and then distributed the x. 420x minus 88x squared plus 4x cubed. All right, so again, we're looking for when is the derivative of volume. So this is the volume of the box. And depending on how big we make x, the volume will change. So the derivative is 420 minus 176x plus 12x squared. So when does this thing equal 0? Okay, so there's a couple options we have here. If you're using a calculator, it's not that bad. We could just use the quadratic formula. A lot of times kids think, oh, I have to factor it. No, you don't have to factor. I would just use a quadratic formula, but since we're saying that when does this equal 0, there is a number that we could divide out of each one of these. If you divide each of them by 4, so I'm going to bring this to the front, divide this by 4, and I get 3x squared minus, this one becomes a 44x, and why do I know this? Because I already did it on my calculator to double check. Divide this by 4, and I get a plus 105, so I just rearranged it to be standard form. And again, you can factor this if you want, but I'm not a big fan of factoring when the numbers are this big, so I just go straight to the quadratic formula. So negative b plus or minus the square root of b squared. I plugged this in, b squared into a calculator. I get 1936 minus 4ac 105 all over 2a. And 2 times a is 6. Let's scroll down here a little bit. Whoop, give us some more room. Okay. So then when you simplify this thing, you're going to end up with, this is a nice perfect square. Plug it in the calculator. You end up with 44 plus or minus 26 over 6. So that gives us two answers. We're going to have that x equals 35, what is this? It's going to be reduced down to like 11.667, or x equals 3. Well, these are our only two options. And again, we could also take, I didn't take the second derivative, but you could take the second derivative here and double check this. It will work out for us. It makes no sense to use this one, 11.667. You can't use that one because this is only 14 wide. If you had two x's that you pulled out, if you pulled out an 11.6 and 11.6, that's 23 inches. That makes no sense. There's only 14 on the side. So the answer is that it's a 3 by 3. This is a 3 by 3 inch square. Whoop, there we go. Oh, I messed up my box. Okay, last problem, and this one is a bit of a doozy. While I've only given 4 examples in these notes, I want to make sure you understand I can't possibly give you an example of every type of problem. You have to just be able to kind of think through this a little bit, try and draw pictures, do the best you can. Okay, let's try this out here. We've got 2 towers that are 30 feet apart. One of them is going to be a smaller one and one of them is going to be a larger one. So we'll say this one is a tower that is 12 feet and this one is a tower that says that it is 28 feet. And how far apart are they? They are 30 feet apart. This distance here is 30 feet. Okay, so what else do we have? There is a stake in the ground. So somewhere along the way, I'm just going to put a little dot here. This represents a stake, and we've got wires from the top of this tower to that stake, and from the top of this tower to this stake here. So where should the stake be placed to use the least amount of wire? So we want to figure out some type of an equation that includes this wire and this wire. So let's call this one, oh, what do we want to call it? Let's call this one W for wire. Let's call this one W sub 1, and we'll call this one W sub 2. So the entire wire is going to equal W sub 1 plus W sub 2. So what we want is to optimize this wire so we have the least amount. So I'm going to write way down here just as a little reminder, well, let's just put it right here, that I'm going to try and figure out when does this thing equal 0. Okay, so here's how we approach this. We've got to figure out a formula for W1 and W2. W2, that's like your taxes. Okay, so here we have this. I'm going to put a little red line right here. And let's call this x. Well, if this is x, then I'm going to use green so you can see the difference. Then this distance right here is what? Well, if the whole thing's 30, then the green one is 30 minus x. Why do we want all this? I'll show you. Because we need a formula for W sub 1, and we need a formula for W sub 2. We're going to use the Pythagorean theorem for this little triangle. If you zoom in and think about this little triangle here, it's x squared plus 12 squared equals w squared, so, or w sub 1 squared. So it means just like the distance formula, Pythagorean theorem, we're going to have the square root of, and then we have x squared plus 12 squared. Next one, the second wire, the second wire is going to be this 28 squared, 28 squared plus 30 minus x squared. So I'm going to put in parentheses 30 minus x squared. Now 12 squared is 144, so I guess you could write this as 144 if you wanted. And then the 28 squared, I've got my calculator here on the side. What's 28 squared? 784. So that is 784. You could write it like that if you want to save ourselves some time. Okay, so now we set up this plus this, so let's write that whole thing out. So I've got that the wire, the total amount of wire is going to be the square root of x squared plus 144 plus the square root of 784 plus, okay, I just saw a mistake. That x is not x squared. Some of you are probably trying to scream at the computer. Like, hey, that's wrong. It's 30 minus x quantity squared because it's this whole thing being squared. Sorry about that. So then over here we have 30 minus x quantity squared. Now, it is possible if you wanted, you could multiply this out. On this particular problem, I already worked this through and kind of saw I got stuck and had to work my way backwards and see I shouldn't have multiplied the 30 minus x quantity squared out. So I'll show you why here in just a minute. Okay, so when we take the derivative of this, so here we're going to have w prime equals, hopefully I gave you enough room on your notes there. So we're going to have this drops down, so I have 2 square root of x squared plus 144, and then times the derivative of the inside, which is going to be 2x plus, okay, now let's do this again. So we have our big fraction here. On bottom, we're going to have 2 square root of 784 plus 30 minus x quantity squared. And then you take the derivative of the inside of this. So the derivative of 784 is 0. So now I'll take the derivative of the quantity squared. So the 2 comes down. And then I have 30 minus x. And then the derivative of the inside of that is times negative 1. Okay, so let's scroll down a little bit, give myself some more room. Before we try and solve this equal to 0, let's clean this up just a little bit. So I have the 2's cancel, so I have x over the square root of x squared plus 144. Now I'm going to say that these 2's cancel. And see this negative 1 here? Makes this become a minus. And then the square root of 30 minus x over the square root of 784 plus 30 minus x quantity squared. That's all underneath this radical, and this is going to equal 0 because this is the derivative. I'm trying to figure out when does the derivative equal 0. Remember that thing from way back here? I'm looking for when does the derivative equal to 0. Set these equal to each other. If once you add this over, so basically I can just do this. I'm going to save myself some writing here. It just basically means I could say this is equal to each other and get rid of this equals 0. So I just added this to the other side. Okay, I'll save me a whole step here. Now, multiply both sides by the denominators. So then I get, actually, you know what? Let's do this. Let's just square both sides right now and clean some things up. So if I square both sides, this gives me x squared over x squared plus 144. See, by squaring both sides, I get rid of the radicals. And then on this side, I have 30 minus x quantity squared over, and now the radical disappears. So 784 plus 30 minus x quantity squared. Okay, so this one's pretty intense problem. There's a lot of algebra skills going on here. The important part was being able to set your problem up. So let's keep going. Now this is just the algebra part. If I multiply both sides, I'm going to have x squared times this whole thing. So I'm going to distribute the x squared. So it's going to be x squared times 784. So 784 x squared plus an x squared times a 30 minus x, not x squared, x quantity squared. Okay, you'll see why I'm doing this in just a second. So now I'll take this whole thing here. So this thing is going to multiply to the x squared and the 144. So the x squared equals x squared times 30 minus x quantity squared plus, and then I have a 144. 144 times 30 minus x quantity squared. So the reason I set this up is so you could identify something really interesting here, and that is, let's go to highlighter, that this x squared here and this x squared times 30 minus x quantity squared, those are the same thing. So they basically cancel each other out. So all I have left is the 784 x squared plus this, or equals this. There's an equal sign. So I found out I could divide both sides by 16. I already worked this out. So I'm going to have divide by 16 on this side. I have 49x squared equals, divide this thing by 16, and you get 36 times 30 minus x quantity squared. And then now what you're left with is the same type of idea as what our problem was before. You're going to have to multiply this whole thing out. We could use quadratic formula. Factoring, I think, would be too long and too hard on this one. But use a quadratic formula, and you're going to come out to get that x equals 9. So if x equals 9, after we use the quadratic formula on this thing, that means your answer is that you place the wire 9 feet away from the shortest, the 12-foot tower. So 9 feet away from that thing. Okay, that was a lot. Let's go through and look at what our strategies are. Here we go. Here's the summary of the lesson. So the strategies that you want to use is, if you can draw a picture, go ahead and draw the picture, because it's really confusing to try and figure out what's going on with all these things. And then identify what's the known and unknown quantities. Things you know, put the numbers down. If you don't know what it is, of course, you're going to use variables. Then we write an equation that is going to be optimized. Remember, if it was volume and we're looking for the largest volume, that's the one we want to figure out for if volume, if that's what we want to optimize, then we say that the v prime would equal 0. That helps us keep track of what we're looking for. Make sure your equation is with only one single variable, so you don't have multiple variables that you're taking the derivative of. And then determine the desired max or min value using calculus techniques, as we've talked about in previous lessons. And then also, I didn't really do an example of this, but sometimes you got to make sure, do you have domain endpoints for your equation, just to verify if your endpoints are part of the max or min. And you'll see that depending on, once in a while we'll have a problem. There's not going to happen very often, but once in a while we'll have a problem where there is a restriction on the domain where x is going to be in between, like 1 and 20. And so you'd also check the endpoints for that. Okay, that's it for this. I hope those examples will at least get you started on these practice problems. You can also check the corrective assignment if you feel like you need more problems. I've created 2 corrective assignments for you to go through if you need it. All right, rock that mastery check, and I'll see you back in Unit 7.